All right. Thanks everyone for joining us today for the Sustaining Barley Webinar Series. This series strives to serve as a forum for conversation and sharing of great ideas to advance sustainability in the malting barley industry. Hopefully, you'll be joining us over the next several months as we bring forward innovative research and practices throughout the supply chain that's helping the malting, brewing, and distilling industries meet their sustainability goals. Our next webinar of this series actually won't occur until after the new year. We'll be taking December off as we have in the past. But I want to thank all of my partners on this series, the Brewing and Malting Barley Research Institute. Gina's on with us today, and the Canadian Malting Barley Technical Centre. I know I saw at least Peter on today. So thank you also to their members and my members of our respective associations, including AMBA, that makes the content possible. So today we actually just have one speaker. Usually we try to bring in a US and a Canadian perspective, but because the US got their baselining barley project or iteration of that done already, we're going to go ahead and devote the full time to our work today. And then we do hope to bring in that Canadian perspective down the road as their project kind of comes to its conclusion as well. So we will have about 40 minutes of presentation and then have a lot of time for Q&A at the end. And I do really encourage folks to turn their camera on, come off mute, and have a discussion with us because that is really what we're hoping to promote in this series. So with that, I'm very excited to introduce our speaker today, Neil Fuller. He is the technical director of the Atlas Sustainable Soils program. AMBA has been working with Neil now for, I think, actually kind of immersively working with you for over a year now.
Yeah.
But today he's going to be presenting on our baselining barley project. Neil studied soil science at Newcastle University, where he graduated with a Bachelor of Science in Agricultural and Environmental Sciences, majoring in crop ecology, ecosystem modeling, and soil microbiology. So he's got a pretty wide breadth of experience. He started a private consultancy company in 1986, and his services have been actively engaged on farming, food, and nutrition projects around the world. Neil is technical lead on agricultural soil carbon accrual for the Future Food Solutions B Carbon Program, which was selected as a finalist for the COP26 Climate Challenge Cup. He presents the popular Soil Safari and Farming, Food, and Climate Change virtual field events and is the author of a number of publications, including the Carbon Farming Manual and the Good Soil Guide, an online reference and knowledge sharing platform for farmers sponsored by Yorkshire Water, which currently has subscribers in over 30 countries. So we have been very blessed at the opportunity to work with Neil on our baselining barley project. I've really enjoyed our time with him and now very excited to kind of share the product of this work that's been ongoing now for the past year. So with that, Neil, I'm going to go ahead and turn it over to you.
Thank you so much, Ashley. It's a great pleasure to be here. It's a great pleasure to have the opportunity to talk through some of these wonderful findings. And I have to start with a massive thank you, not just to Ashley, but to the team and to all the participants on this particular program. I know it's been a challenge. And I know it has been a tricky negotiation to make sure that everybody's been taken care of and all the data has been lined up. But this really couldn't happen without all your participation. And the information you've been able to share has been fantastic. It has delivered some really positive messages. It's got some really powerful background metrics that show you're doing a remarkable job. And from my perspective, striding the world with a big shiny spade, digging holes in the ground, you guys are right at the top of the capability for delivering on the environmental side of malting barley production. So from me, a huge round of applause. Great thanks. And let me show you a little bit more about what's going on. Okay, I'd like to start with a bit of an overview with regard to the program and how it sort of came about. And if at any stage there's anything that crops up with regard to the story or the information or the sorry, I'm just struggling with my presentation here. It won't run. That's going to slow me down a bit. Um, Here we go. I apologize for that. What a glitch. Um, okay, just to give you a little bit of an overview, and as I say, if you've got questions, drop them in the chat or drop them in the comments, and we'll unwind them as we get going. So the big picture, understanding the environmental impact of malting barley. The primary platform for working on this one is the Science Based Targets Initiative. It's all about emissions and decarbonisation, and it groups emissions into broad categories. Scope 1 and 2 are all about energy generation, mostly electricity, but it's emissions to do with the energy side of things, on or off organisations. The scope 3 bit is all about production emissions. That's where we're going to operate with regard to the malting barley. That's the inputs, the outputs with regard to what we grow at farm level. And then there's a scope 4 set, which goes beyond value chain. And that's worth considering too, because there's lots we can do within the framework of this particular program that will reach from soil to supermarket and beyond. And that's part of the really powerful message I think that's coming out of this piece of work. There's a second fraction on this one, and that is just looking at the broader environmental implications using the Sustainable Agriculture Initiative. Now, this is more about nature restoration, regeneration, and it gives us 5 key critical impact areas: soil health, water quality, climate, so it sort of extends what science-based targets are doing. Biodiversity, which is a real driver at the moment, particularly with regard to engagement. And then there's a little bit on the socio-economic, which is all about livelihoods. We've got to make sure that everybody thrives and survives through this. Both programs require baseline values to be generated, and those baseline values create action plans. Now, those action plans, essentially what we're able to do is to set targets and timelines. Where are we? Where do we want to be? What is the exciting path for us to take? And within those targets and timelines, we can then structure strategies for emissions reductions, emissions removals, and any specific regenerative targets, soil and water conservation, nature restoration, the big picture stuff. So all that is sitting behind the formulation of this particular program. Okay, so what does the science-based targets allow us to do and how does it unfold? I'd like to illustrate that by drawing a very straightforward value chain. So here we are at farm level. We're growing our malting barley. We're doing our best to hit our yield and our quality and our consistency targets. Come harvest, we'll hand that grain over, maybe to a merchant or an aggregator who might dry it, store it, transport it to a maltster. They're going to convert that barley into some wonderful ingredient that's going to get into the hands of the brewing and distilling sector. They're going to conjure up all manner of dark arts and turn that into the beverage that we may know, beers and spirits. The important bit about the science-based targets is this. It says, understand the emissions that you generate at farm level, because those emissions, scope 3 production emissions, will track right the way through the value proposition that we've got here. Every organization that handles that barley is going to have to deal with some of that scope 3. And the farm's got a really long reach. If we put just 1 kilo, 2 pounds of barley in at one end of this value proposition, we're going to get quite a few pints of beer out at the other end. And every single one of those pints of beer is going to carry a little bit of that scope 3 emission that we generated at farm level. So science-based targets says, understand where you are and then put a plan in place to reduce the baseline value over time. And we've got quite a clear guidance with regard to targets and timelines. What is it we need to achieve? Now, this gets even more important when we talk about using specific grain from specific soils or specific fields to go into spirits that then may have specific characteristics. This barley's got a lot, it carries a lot of weight with it. And science-based target says that's okay, don't worry about it. Simply understand where your emissions lie, see where your liabilities are, and then let's put a framework around sorting that out. So for the spirits that's just popped up on the screen, the big bit of carbon liability is barley farming. Science-based targets turn around and say, okay, let's put together a pathway for everybody in this value proposition that reduces our emissions by just over 4% a year. And the science behind the science-based targets is a global cooling target. We've got two frameworks within this. One is emissions reductions. That's all about substitution, decarbonisation, moving to low emissions technologies. And we've got a removals piece. Now, that's quite unique to the land-based sector because that means that we can deploy techniques that allow us to neutralize greenhouse gas. So not only do we reduce, and we put a barley through this value proposition at a lower embodied carbon value, we can take care of some of the carbon that everybody else has got to deal with as well. And essentially, what's happened then, this science-based targets repositioned agriculture. It's redrawn the value chain. It's put us all on this pathway to limit surface temperature on the planet going up above 1.5 degrees above pre-industrial. And essentially, then, our reductions targets are a real driving force. Everybody is on this pathway. Everybody has got to get to the end, and everybody's got to hit these annual reductions. So we're all in this together. And the really smart bit about this one is that industry that supports us is decarbonising as fast as we are, and our strategies are being loaded with really smart technology, which will allow us to decarbonise. The unifying force for agriculture is that we can engage in the removals piece. So we can pull carbon out of the atmosphere and we can neutralize greenhouse gases. We can also bring in the sustainable agriculture ambitions and say, right now, we can extend the sphere of influence of this malting barley. It's not just malt that's going into beer and spirits. We can actually talk about sustainability and resilience. We can add layers of biodiversity, nature restoration. We can talk about health and well-being, not just about us, but the planet, the soil, the ecosystems that we work with and how they function. We can talk about soil and water conservation. We can talk about climate. We can talk about nature restoration. And all that's because we brought together these two frameworks: science-based targets, sustainable ag. Everything pivots around soil. And I've got to be honest, soil is where I work. It's a really dull, difficult topic to get excited about. The nice bit about pulling these two platforms together is that the barley can now be associated with, for example, high biodiversity, cover cropping, functional field margins, things that are very, very easy to associate with and engage with because they're full of bees, butterflies, colour and life. And if we get this right at scale, we start to deliver soil and water conservation at landscape. And when we start to put that behind our barley production, this isn't just an emissions program. What we've actually done is we've changed the value proposition in the barley, which has changed the value proposition in the beer. We're now able to say to everybody that takes a sip of one of these pints, you are actively rebuilding and restoring nature. You are actively cooling down the planet, and we're doing it one sip of beer at a time. That's the scale and the reach of this particular program. Okay, nuts and bolts. Where does it start and how do we get there? We're actually going to just look at barley in isolation. We're going to consider it as a crop rather than a whole farm carbon audit, and we're going to look at what we put into growing that crop. Now, you very kindly shared some primary data, and essentially it's in three big groups. The energy side of things, fuel for tractors and combining, the materials, things like fertilizers, crop protection chemistry, and the residue. What happens to the straw as it begins to break down? And many of you very kindly submitted data in a digital format that we could then take all the right information up for how the barley was grown for the baseline year, drive that through a calculations platform known as Cool Farm Tool, which attaches emissions factors to all the various materials and activities. It does also model soil carbon change. Although I've got to be honest, right now, we're going to keep that in the background and not talk too much about it. We're just going to focus on production emissions because whatever comes off the field, whatever comes out of that barley box, we want to work out the scope 3 production emission, the global warming potential of that. And just to share the first glimpse of data, this is your live emissions data. It's a chart that shows barley yield against absolute emissions. So that's emissions per unit of area. And the very first thing I want to do is to put it in context. I've been doing this for quite a while now, and I would like to share some data from other regions. So the green boxes that are popping up here, this is barley being grown in Ireland. So it's a warm, wet, high yield environment, high disease pressure. We've got barley that's being grown in England and Scotland in colder, drier, more northern reaches, and then two dryland agriculture, short summer, short hot summer, long cold winter environments, and just showing you the data there. These are all the same units, they're all the same process, they're all the same data sets, they're just from different regions. And the first thing I wanted to show you was your data strides that really nicely. So you're not isolated, you're not out on your own, there's no region specific doing well or not doing so well. You're actually right in the middle of this mix. And that for me was a really positive first message to come out of this. Now, what we really need to do now is to understand the data and explain it in a little bit more detail. And the charts that you're looking at, I find a little bit complex. So what we tend to do is illustrate the data using a dial gauge. Now, there are two reasons for this. One is we can share complex data and make it look quite nice. The other is we can maintain anonymity and integrity. The dial gauge is calibrated by the group data set. So we find the group maximum, we can show that on the dial gauge. We find the group minimum, we can show that on the gauge. We can calculate the group average and put a confidence interval around that and put that on the dial gauge too. It means then that that gauge is carrying all the information in the chart, but is very, very straightforward to interpret. When we then look at a specific farm value, so we load up any particular region, any particular farm, any particular participant, we take the farm value, we can load that into the dial gauge, and the farm can see exactly where they are within the group capability without knowing what anybody else is doing. So you maintain the anonymity and the integrity of the data, but you allow each individual farm to chart progress, monitor their place within the group, understand their direction of travel. And that allows us to share this information at quite a high level and to drain a lot of value out of the calculations. So what do we do with these emissions? We can show them as absolute emissions. These are per unit of area, and they tend to be quite stable year on year. What we're really interested in is relative emissions. They are emissions per unit of yield, so per bushel, per pound, per kilo, or per ton. And the reason we're interested in that, again, I'm going to share a bit of my data. This is how emissions on one of my trial sites changed for spring malting barley over the last few years. And that's not actually to do with management. That's to do with season. It's all about mirroring the yield response because the yield is effectively diluting or concentrating the emissions that we're working with. So the relative emissions chart seasonal impact. Absolute emissions show us what total management is up to. Both sets of emissions values have to show the science-based targets alignment in reduction. The final bit that we can play with are net emissions. Now, I'm going to be honest, I'm going to totally ignore that for now. But net emissions tend to use a modelled carbon drawdown and take that off your production emissions and give you a net value. The difficulty with that is that unless the drawdown values are validated either through direct measurement or through some other process, it's a little bit like guesswork, and I'd rather we didn't get into that. I would rather we were quite upfront with regard to this is what our production emissions are, this is what's causing them, and this is how we're going to manage them. And that's the next bit of the presentation. The data that we've got actually falls into two superb sets. We've got an irrigated set and we've got a rain-fed set. There's no discrimination in terms of one better than the other. I'm going to talk you through both sets. It's just that they do have slightly different characteristics. One of the big defining ones is that there's yield and energy differences between the two data sets. And if we put them together, a combined average data set doesn't have a lot of meaning. If we take the average data set from the rain-fed crop, we can actually build out what that average value is made of. There's an energy component, which is mainly fuel use for machinery here. There's a little bit on haulage, that is getting materials to and from the farm. There's a chunk that goes on residue. So if you're chopping and incorporating straw, Cool Farm Tool treats that like an organic input, and there's a bit of an emission associated with that. We've got our crop protection chemistry. We've got our nitrogen fertilizer in terms of the product that's being used. And then we've got the nitrogen emissions related to in-field breakdown of the product. We can categorize these in terms of are the inputs, are the energy, are they residue related? And we can categorize them in terms of their greenhouse gases. So the big bit is actually the greenhouse gas known as nitrous oxide. And it, from an agricultural point of view, is the big challenge for the cropping sector. Once we've got that information, we can start to play with all sorts of ideas with regard to how do we reduce these emissions? What do we need to do to build strategies around the targets and timelines? How easy is this going to be to actually manage away? And the whole point of this is that it's actually being driven by the data. Now, we'll feed this information back to individual farmers, and we report this again using the dial gauges. So the average value and the gauges are using the entire group data set. You're just looking at the average values for the rain-fed component at this point in time. You've got the absolute values on the left-hand side and the relative values on the right-hand side. Now, the relative values are what supply chains are going to be worried about because they're going to trade tons of barley and each ton is going to have an emission value associated with it. But what we need at farm level are the individual components of that value so that we can understand how we mitigate, we abate, we reduce, we remove, we neutralize. And I just wanted to illustrate that for the group average rain-fed data set. You've got a haulage component, we've got our crop protection. Residue is making a big part on this one, and I'm more than happy for you to challenge me on that one and say, look, should we be incorporating, should we be removing straw? The driver, the real driver, is fertilizer. It's the nitrogen product we choose to use and what happens after we've used it. And I want to go into that in a little bit more detail. Again, use the data to tell the story and then unwind some of the potential solutions from that. Okay, so let's look at some of the primary data you very kindly shared with us. I'm going to start by looking at the energy side of things. So let's pick on field operations. That's a bit of, that's probably the biggest bit of the energy component in this particular carbon value. What data do we need? Well, the very, very basic data set would be how much fuel did you use and what area of crop did you grow? And that would give us an emission from the fuel per unit of area or per ton or per bushel. And that's baseline. But if we knew a little bit more, and that's why the data set, the primary data set becomes so important. If we knew a little bit more about cultivation and tillage, planting and harvesting, the applications that go on for crop protection, for fertilizer, for lime, for nutrient management, we can actually do a lot more. We can actually begin to chart out the various activities and where their carbon emissions lie. And that will allow us to ask questions. Do we or do we not change a tillage practice? Do we or do we not change a fuel type or a machine? Is there anything that's going to come from this that can help us understand what's going on? And one of the comments I have to make is that if we don't have actual values, Cool Farm Tool will put in estimates. And looking at farms where we've got actual values and looking at farms where we're using estimated values, Cool Farm Tool seems to be overestimating compared to what your real data sets are by about 20 to 24%. So if we get a bit more data, a little bit more granularity in that primary data set, we're going to help to fine tune these results. So they're only going to get better if we can move in that particular direction. There's a little bit more we can do as well. The more information we've got about the field operations, the more we can start to bring in our sustainable ambitions. So if we were to look, for example, at minimizing soil disturbance, from a good data set, we can actually calculate soil tillage intensity rating. That's a metric that we can report on. It's not part of science-based targets, it's not part of your emissions fraction, but what it does do, it puts a lot of strength into the story that says the way we grow barley is really good for us, it's really good for the planet, it's really good for soil and water conservation, because we can support the outcomes for the Sustainable Agriculture Initiative, as well as supporting the key ambitions of the science-based targets. And that, for me, draws extra value from the data collection process, but it also builds a stronger story for your marketeering, for your ambition, for your engagement. You can stand up and say, this is what we're doing, and we've got the numbers to prove it. Now, if we look a little bit more detail, because we need to start addressing some of the bigger bits, let's look at nitrogen fertilizer. That's the orange bit on the pie chart. What is the basic minimum data set we need? Well, we need to know how much total nitrogen you applied. We really need to know the area it went on so we can work out pounds of nitrogen per acre or pounds of nitrogen per bushel, and that would pretty much give us an estimated value, but we do need more. If we know the type of nitrogen, we can fine tune that emissions outcome, because the different types of nitrogen and where they're made carry different emissions factors. If we know a little bit more, application rates, timings, do we put on other nutrients, we can build additional metrics. So we go beyond the carbon story into nitrogen use efficiency. And that helps us understand varietal selection. It helps us to choose our fertilizers. It helps us to understand if we decide to go from one type of fertilizer, let's say urea, and there's nothing wrong with urea, I'm just using it as an example. If we then transition to calcium ammonium nitrate, what does that mean in terms of crop performance, cost, environmental impact, carbon footprint? We can ask those questions before committing to making that kind of a decision, because the data set that you provided has got that information in. We can interrogate that data. We can come up with some really smart interventions for you. The big bit, and this is going to take a little bit of explaining, I apologize for that one. The big bit of the emission is this in-field fraction. And that's all about, yes, the total amount of nitrogen we put on, and the type of nitrogen very definitely influences this. But there's a little bit of science behind this, and it's all about how nitrogen breaks down once it's been applied. And I'm going to draw you a little picture on this one just to try and illustrate this in a little bit more detail. We take our barley plant, we pop it in the ground, and we introduce a little bit of nitrogen. I'm going to start with urea. As I say, nothing wrong with urea. Let's drop it in the ground and see what it does. It's quite unstable when it comes into contact with water, breaks down quite quickly to produce ammonium through the process of hydrolysis. Ammonium will break down under low temperature decomposition to produce nitrate. Now, both ammonium and nitrate are plant food, so the plant will draw those in, make good use of them, build protein, boost yield, do all the good stuff. But if the nitrate's not picked up quickly enough, there is a risk that it will be converted to nitrous oxide. And that step goes from nitrate to nitrite and then breaks down a little bit further. At every stage in this low temperature decomposition, there is this risk. This nitrous oxide, N2O, can be lost. And the driving force behind that is that actually what we need from an interventions point of view is something that deals with the global warming potential of nitrous oxide. And the issue we've got is this: 1 kilo, 1 pound nitrous oxide has a global warming potential nearly 300 times greater than CO2. So we don't need much of it to create a problem. So the question we do need answered is, has your nitrogen got any sort of inhibitor added to it? Now, we might think of inhibitors as volatilization inhibitors for ammonia off-gassing, and that's great, but ammonia is not a greenhouse gas. We need inhibitors that will deal with this nitrous oxide component. There are some out and about, and the neat bit from an agricultural point of view, from an agronomic decisions point of view, the inhibitors are making nitrogen fertilizer work better. So they're actually paying for themselves in improved nitrogen use efficiency and yield uplift, but they're delivering significant emissions reductions. Now, if you haven't done your baseline and you haven't done your background carbon calculations, that benefit will be lost to you. And that's the next bit of the story I would like to illustrate, how we understand what these interventions actually do. Okay, just quickly going back to the interpretation side of things, I'm going to bring in the irrigation story. So this is the group average for the irrigated crop data set. We send that information across to our carbon calculator. We reset the system. We run the calculations again. We get a slightly different picture. Now what we've got is a bigger energy component, and I've put it in blue so we can see it's all about irrigation, but essentially it's the energy that's driving the pumps. And it just changes the energy to input ratio, and it changes the carbon dioxide to nitrous oxide ratio. When we look at the data sets side by side, we can see that actually, if we deal with the individual components of those group averages, we can have a really good impact on those carbon numbers straight away. So the bar chart now, we've moved from the absolute emissions, we're now showing you the relative emissions for the baseline averages. If we swap to renewable energy to drive the irrigation pumps, there is no difference in relative emissions between rain-fed and irrigated crops. If we move from a conventional, what we would think of as a grey fertilizer, to a green nitrogen, both data sets show significant improvement. If we introduce inhibitors, both data sets show significant improvements. If we put nitrogen fixing microbes onto the seed or onto the soil, both data sets show superb improvements. And if we introduce fresh genetics, new varieties, better biotic and abiotic resistance mechanisms through our conventional feeding programs, you can see that actually the driving source behind these emissions improves whether you're irrigated or non-irrigated. And I just wanted to make that a point, re-emphasize that point. There is no real issue between are we rain-fed or are we irrigated. There are challenges in both sets, but all the data shows that you can very, very effectively manage all these emissions in the right direction, and full credit to you for actually putting that together. Okay, so where do we get this information from, and what is it we're trying to do? How do we unpack this data and make it usable? The aim is to use these targets and timelines to change our management, but we change our management without compromising yield or quality. And I'm going to throw something a little bit left field at you. I do my agronomy in one of these things with a hyperspectral sensor flying over crops at 200 miles an hour. And I want to show you why. It's a lot of fun, but it's also very informative. This is an image from a little bit back now, one of our trial fields, looking at 4 individual varieties. The boxes of individual varieties are 4 meters by 20 meters, and they've all got individual treatments. So I'm on the ground there putting different nitrogen and crop protection chemistry on there. The sensor on the aircraft is tuned to look at red edge inflection point. The more red in the image, the more stress there is in the crop. Early on in the growth stage 30-32, really dry season, no disease pressure, all the treatments not really shining out. We get to flag leaf and then ear emergence, and individual treatments start to shine out through the sensors, the hyperspectral sensors, way before I can detect anything at ground level. And the neat bit about the data set is there's a massively strong correlation between what the aircraft sensors can see and the final yield of these individual treatments, the varieties and the inputs, the nitrogen types and the crop protection that we put on there. And that then informs carbon metrics. So this is not just about agronomy, this is about showing us climate impact. And if I unwind this a little bit at ground level, there are a couple of things I wanted to illustrate, and we will go through this in a bit more detail when we meet again next year. But I just wanted to show you one of the big driving forces, genetics, some massive improvements in terms of conventional breeding, putting resistance into drought or drought tolerance, if you want to put it that way around, resistance to drought stress, and looking at disease pressure, looking at how plants actually handle nitrogen. Some of the modern varieties have superb nitrogen use efficiency characteristics. Now, it's quite easy to detect a variety that outperforms the standard. So we've got variety 1 as our group standard, but variety 3 shows it's doing pretty well, and variety 6 and variety 7 show they're doing pretty well. So by eye, just looking at yield data, I can say, yep, okay, we've got something worth looking at. This next bit, if you haven't got your carbon numbers, this next bit is totally invisible to you. This is what the carbon values are like for these individual varieties. And it's being driven by improvements in genetics. It's being driven by the fact that these varieties are just a little bit more efficient, effective at fighting disease, harvesting nutrition, making good sense of water. And what you're actually looking at there are significant emissions reductions based on improvements in performance. This is why relative emissions are so important in terms of reporting. If we can get those crops to grow just a little bit more off the same level of inputs, that's the same as reducing our overall emission. So that's our variety story. What else can we do? Well, we could take variety 3 and then we could add low emissions nitrogen, additional inhibitors, biological nitrogen fixers, for example, or stress promoters. And what we can then do is run the trials again or in parallel with these high performance genetics and say, okay, now what have you been able to do? If we put a stack of agronomic interventions in place, now this gets harder for us to find the differences, for us to choose the winners. Just looking at yield from this particular trial, there is no statistically significant difference between the treatments. So if I was to present this information to a farm or an agronomist and say, okay, I need you to pick the winner, I would suggest they'd show me the door and tell me to clear off because there isn't a winner in this one, just looking at yield. And you'd be right. But again, if you haven't got your carbon numbers, this next bit's invisible. This is what these interventions are doing for the baseline emission. If we move to a biological seed treatment, yield stays about the same. We drop our emissions. We introduce our biological nitrogen and additional nutrition. We see improvements in crop performance, marginal, but improvements in emissions significant. We move from grey to green fertilizer. We introduce our inhibitors. And now what you've got is a series of management actions or interventions that farms could choose to use that will maintain yield or improve their yield marginally, but hit their targets. And where do we need to be? Well, this is our 2030 target for the group. And this is our 2040 target for the group. Now, the emissions values can be reached today using the technologies that we've got on farm. But the background research, the baseline program is saying there's a chunk of carbon that actually is going to resist all our reductions. And that's where we've got to get into removals. We've got to get to things like cover crops. We've got to look at drawing down atmospheric carbon and look at neutralization, looking at mineral techniques for taking atmospheric carbon and converting it into inert forms, or taking nitrous oxide and getting that to break down into a form that is no longer challenging from a climate point of view. So the story is there, the data is there. The position of the group is absolutely superb, not just within the US, but within the world stage. You're doing incredibly well. Plenty of scope for addressing these emissions, lots of options in terms of interventions, lots of capability with regard to doing all the good bits that we need to hit yield, quality, consistency, engage with every player on the supply chain, show our end users, our consumers, that we're doing a really good thing to restore, rebuild, and repair the planet, and that as they invest in the beers and the spirits that we produce, they are actively promoting this change. That's it from me. I know we've covered a lot of things, but I just wanted to leave you with one particular thought, and it's this. The world needs inspiration. The world needs clear proof that inclusive, rapid, large-scale change is possible if humanity is to achieve net zero and its broader climate ambitions, environmental ambitions in time. My belief is that you have clearly demonstrated that this is your gift to give. Thank you.
Excellent. Thank you very much, Neil. With that, I would welcome people to go ahead and either come off mute and ask questions, or I will try to also monitor the chat. I did want to just take an opportunity real quick to say thank you to the American Malting Barley Association members that contributed data to this effort. It
Yeah,
certainly was no easy task to kind of dive into this world of data collection and making sure that we had it in an appropriate format that Neil could use. And that meant going to the farmers that you contract with and securing that data. And we all know how much of a hot topic that is right now about
yeah,
ownership of data and utilization of it. So just want to thank my AMBA members that did contribute data to this effort because I do think that that kind of diverse perspectives and different data sets coming from different regions really helped make this a robust
yeah,
situation. So many thanks to those members and everyone that was involved in those companies that participated with this. And also just want to shout out to AMBA for the support of this project to get it off the ground. And
yeah.
for those of you on the sustainability committee, we're going to meet actually immediately after this to chat about what's next if we want to keep doing this similar work. So look forward to that conversation. But for now, if anyone has questions for Neil, I welcome you to go ahead and ask them. Sean Clare is asking, did your bar graph comparing irrigated and rain-fed carbon intensity imply that genetics will have the biggest impact, or were they compounding and genetics would have the smallest impact?
Thank you for that one. It's compounding and it's going to depend a little bit on the reach of the genetics. But I was just looking, for example, at spring malting barley varieties. We've done a little bit of work with winter malting barley varieties. And where we're seeing, and we've got some from the Nordic states, for example, that have encoded barley yellow dwarf virus tolerance into winter barley, and we're seeing between 10 and 14% yield uplift off the same level of input. Now, if we could do that consistently, that would be a significant impact that would rival introducing inhibitors, nitrogen fixing microbes, all that kind of thing. So we get usually from a breeding point of view, and forgive me if I'm talking to anybody who actually knows about breeding because I don't, but usually breeding gives us incremental yield, and it's 2 or 3%, something really smart, usually because we've got increased resistance against the disease or an insect. Some of these new genetics or these new varieties with broader genetics are showing step changes. So it's not 2 or 3%, it's 10, 12, 14% yield change. I didn't want to put that into the graph initially, just in case that wasn't appropriate for you. But I think there's a mass of benefit to come from varietal selection, from genetics for developing biotic and abiotic tolerance, specifically the way our weeds, our pests, our diseases, and our climate is throwing more challenge at crops.
Great. Thanks, Neil. Brian, go to you next.
Yeah, Neil, great presentation, most interesting,
Thank
very
you.
complicated, of course, and obviously subject to some considerable error in some instances, especially on individual farms and so on. But I think it's really useful. But I would ask you, all those agronomic interventions that show basically not changing the yield much at all, but lowering the carbon intensity, all of those things cost money. So
Yes.
what about the cost of doing those things for the farmer who doesn't get any more yield? How do you rectify that?
That is the real challenge. Thanks, Brian. What we're really hoping, and this is where we're doing so much in terms of developmental trials work and exploring agronomic options. What we really need is for these interventions to cover their cost by improving crop performance, either by delivering more yield or by making savings. So, for example, the biological nitrogen materials are potentially delivering, let's say, 10 or 15 pounds of nitrogen per acre. So there's a potential saving in total fertilizer. There's a cost associated with putting the biological on, and the yield may not change. But if we run the numbers appropriately, what we may have done is drop the emissions, maintain the yield and quality, swap out a little bit of conventional fertilizer for biological fertilizer and not actually cost the farm anything. Now, we won't know enough about that until some of these interventions are really in practice. But the data set from the baselining program has given us a fantastic insight into the scenario thinking around this. If we can save 20 kilos, 20 pounds of nitrogen by doing this intervention, there's a saving in cost. Does that cost saving cover the new intervention and what happens to yield? And I'm very, very mindful of that. Very, very definitely. We cannot be asking farms to be spending more money on this. What we can be looking at is making farms as efficient and effective as possible, nudging that yield up year on year, making those inputs work as effectively as possible. And for me, the data that you've shared is a great insight into how we can make that happen. But it is a very, very sensitive topic. And yes, costing has to be part of the factoring. It is one of the five critical impact areas for the sustainable agriculture incentive. We have to be looking at the livelihood side of things. We can't be compromising farm performance. We can't be adding cost to the farms for an environmental ambition unless everybody sees a benefit. And that is what this program is all about. It's delivering the data that drives the decisions that show that everybody wins from this, not one person is penalized.
I'll also just jump in too and say that in January, our webinar is actually going to feature just some preliminary results off the optimizing nitrogen trial that's being conducted across Idaho, Montana, North Dakota. And that group is actually looking at some of these alternative nitrogen sources and inhibitors and doing a little bit of economic analysis based on, okay, yes, we might be able to drive nitrogen or might be able to drive emissions down. We might even have better productivity in the field, but from a profitability standpoint, do these items pencil out? And so we will actually hopefully get to see some of those results in January and whether or not some of these interventions are going to pay off for farmers. So we'll have some really sound data coming from our fields on some of those questions. What other questions are out there for Neil? It's a lot to digest.
It is. I apologize. It is a lot to digest.
Well, and I'll just call out too that we really wanted to queue up with this webinar because for those of you that will be in San Diego with us at the Barley Improvement Conference in January, Neil will be doing even a deeper dive and actually starting to look at those interventions and recommendations for our industry as we move forward. And so this is kind of giving you an opportunity to start diving into the results, but then hopefully actually turning those ideas into practical applications in the field as we look ahead to San Diego. Anything else from the group?
There's a lovely one just popped into the chat. Thank you, Sean. Do we think nitrogen use efficiency or disease resistance will have a bigger impact on carbon reduction? Straight off the top of my head, my feeling is it's going to be nitrogen use efficiency. Nitrogen's probably 75% of your baseline emission. The crop protection chemistry that we would put in to maintain clean, healthy plants, although the individual ingredients that we would use have quite hefty carbon intensity values, we don't use much of them. And because they fight disease, they give us yield uplift. And as a result, the disease resistance piece and its impact on carbon emissions isn't as significant, in my opinion, as nitrogen use efficiency. I think if we can get bigger, bolder crops off a 10% or a 20% lower nitrogen rate, you will see the needle on those dials change really quickly. If we were to drop our crop protection by 20% because our variety is more resistant to disease, those needles are hardly going to change. The big bit is going to be if we can combine the two, nitrogen use efficiency and disease resistance, and get a significant yield uplift. That's my hope. What I think the promise of our barley genetics programs have got. I think there's real scope to combine them two. The bit also that will make a difference is going to be water use efficiency. So if we've got crops in a dryland environment, rain fed, that are better at scavenging water because they've got bigger root systems or they've got a better communication with beneficial microbes in the soil, then you're going to start to see significant gains within the context of the farm's ecosystem. And that might be a bit specific and it might get very regional, but I do think there are real gains there. None of it should be overlooked. Every incremental gain is going to be essential if we're going to need to reach our ambitions. But to answer the question, I think nitrogen is the big one for me. Whether it's nitrogen products, nitrogen applications, precision nitrogen, or genetic nitrogen harvesting, metabolism, and all the good stuff that plants can do. But I think nitrogen is the big driver. And a final comment from me. I'm a very, very old person. You can probably tell by the white sheen on my head. In my lifetime, global agriculture has doubled the amount of food it produces per cultivated acre. And it's done that because it's had access to synthetic nitrogen. It means that we're feeding an enormous amount of people based on our nitrogen and our nitrogen management. But nitrogen is the biggest bit of our environmental impact too. And nitrogen is going to be quite a difficult conundrum, complex scenario to play out because we simply can't stop using nitrogen. And we simply don't have alternatives that will do what current nitrogen is doing at this point in time. So for me, I think that the nitrogen side of things is going to be a real challenge.
Thanks, Neil. Open it up just for any last questions. All right, I'm going to go ahead and stop the recording then.